Okay, guys, let's start. So let me recall. The previous time I started discussion of finite abelian groups. Today I want to continue with finite abelian groups. And well, what I want to talk about now is the structure of the n star. Well, as you may have noticed, this group is a finite abelian group. And as we already know, it must be, well, it can be presented as a product of cyclic groups. But it's not obvious how to decompose this group into a product of cyclic ones. So I want to address this question today. And the first tool I need is multiplicative version of the Chinese remainder theorem. So multiplicative version of the Chinese remainder theorem. Suppose we're given two positive integers, coprime, positive integers n and m. Then we have two groups, zmn star and zm star times zn star. It's very similar to the thing we had in the regular Chinese remainder theorem. Now the only difference that we have star here. And we have a map from left to right, which takes any remainder to a pair, k modular m, k modular n. Exactly the same map as before. But now, this is a group with respect to multiplication. And these two guys are the groups with respect to multiplication. And the claim says that this map is also an isomorphism of groups. So this is the multiplicative version of the Chinese remainder theorem. Okay. Now, if we want to prove the result, we need to prove what? We need to prove two things. First of all, that this map is a bijection, and the second thing, that this map preserves an operation. Okay? In this case, the proof will be easier than in the previous case, because we already know that if we take the map phi from zmn to zm times zn, which is given by the map k goes to k modular m and k modular n, then this map is an isomorphism of groups with operation given by addition. So we already know that this is a bijection. Bijection by the usual Chinese remainder theorem. But now, this thing is a subset here, and this thing is a subset here. So what do we have here? So this is zmn, this is zm times zn, and this guy is a subset here, and this guy is a subset here, and we have a bijection on a larger set. So in order to have a bijection on the smaller sets, we just need to show that, well, all the elements here from this subset under this map goes to all the elements here in this subset. So now, what does it mean that the remainder k belongs to this subset? So k belongs to zmn star. By definition, if and only if k and mn are coprime. So there is no common factors between k and m times n. But what does it mean that this pair belongs to this subset? It means that k belongs to zm star, well, k modular m belongs to zm star, and k modular n belongs to zn star. But this is the same thing, so k, let me write it down here. So this is the same thing as to say that k and m are coprime and k and n are coprime. Okay? But now, you see we have two conditions. The condition number one is this one, and it says that the element k is here. So the condition number two consists of two ones, this and this, and they describe a pair that belongs here. So if we want to have a bijection here between this subset and this subset, we want to prove that this condition holds if and only if these two conditions hold. But this should be clear by the definition, because if there is no common factor between k and the product, there is no common factor between k and each factor, and vice versa. If there is no common factor between k and m and n, there is no common factor between k and the product. So these two conditions are equivalent. So that's why the element k belongs to this subset if and only if this pair belongs to this subset. This simply says that, if you restrict this map to this subset, you will get a bijection between these two subsets. So this is how it can be proved using this bijection. Okay, who was able to follow? Are there any questions regarding this statement? Okay, the second part requires to prove that this map is a homomorphism with respect to multiplication. So, by the way, who thinks that it's clear that this map is a homomorphism with respect to multiplication? Just in case. Okay, but let me show you how to prove this. So, what we need to show that if we are given two elements k1 and k2, we can first take the product modular m times n and then apply phi capital, or we could apply phi capital to each element and then use the operation in the right hand side. And now we want to prove that these two are the same. So this is just by definition means that we have a homomorphism. Now, let's compute by definition what's given here. So if we have k1 times k2 modular mn, then we should map this element to this pair. So let's say left-hand side and the right-hand side. So the left-hand side, just by definition, is what? k1 times k2 modular m times n, and then modular m. And the second factor will be k1 times k2 modular m times n, and then modular n. So this is the image of this element under phi capital. But now, if you take the remainder modular mn and then a remainder modular m, the result will be the same as just to take the remainder modular m. And the same thing is here. So the result will be this. Just by the properties of remainders. Now, but if we compute the right-hand side, then just by definition, this thing is k1 modular m, k1 modular n times, and this thing is k2 modular m, k2 modular n. And by definition, by the definition of the direct product, if you want to multiply this pair with this pair, you should multiply the first elements and then the second elements. But how do you multiply the first elements? You just apply multiplication modular m, so the result will be exactly this expression. And if you multiply the second elements, the result will be exactly this expression. So as you can see, there is no difference between the right-hand side and the left-hand side, so they are the same. So that's why this equality holds, and this thing is a homomorphism. And since it's a bijection, it's an isomorphism. Okay, who was able to follow, just in case? Okay, are there any questions? Now I have a question to you. Where did we use this property? So it seems like we never used this. Is it true?
The Chinese Riemann theorem requires m and m be
exactly.
prime.
This is the place where we need this condition. Because in order to have an isomorphism here with respect to addition, well, at least to have a bijection here, we have to take two coprime numbers, because if this is not true, then this fails to be true. Okay. So now, if we're given, let's say, Zn star, what we could do, we could factor the integer n into the product of primes. Okay, where pi is a prime. And k1, kr are positive integers. Then, using the Chinese remainder theorem, in this form, we see that we can split this thing into the product of this form. Okay? So this is the first step in order to describe this thing as a product of cyclic groups. So now the question is how to represent each factor here as a direct product of cyclic groups. And the main question is it true that each factor here is already cyclic? I mean, here, what's the difference? Here we have an arbitrary integer, and here the integer is just a power of prime. So is it true that if you are given a power of prime, then this group is cyclic? Well, the answer, this is almost true. So let me show you what it actually means. What usually happens when you're given a prime, there are two different worlds. First of all, you have to study odd primes and then even primes. Okay. Okay, yeah, you know, this is the department of even primes, like the department of number theory and sub-department of even primes numbers. Okay, so in case of odd primes, the answer is yes, this group is cyclic. So I'm not going to prove this claim. I just want to formulate the claim itself. So suppose P is an odd prime number. Then Z p to the k star is cyclic. And if it's cyclic, then how many elements do we have here? No, we have p to the k.
No, just p minus 1.
Too few and too many. P to the k minus p to the k minus 1. Because how many elements do we have here without star? We have p to the k elements, okay? From 0 to p to the k minus 1. But now we have to exclude all the elements with this, having common factor with p to the k. So we have to exclude all the numbers divisible by p. But, well, how do they look like? Well, they are p, 2p, 3p, etc. And what is the final one? The final one will be p to the k minus 1 times p. So we have exactly p to the k minus 1 of them. Okay, who was able to follow this? Who thinks that I should write this on a whiteboard? Okay, so if we're given z p to the k, it has 0, 1, and so on, and p to the k minus 1. These are the elements of this guy. But now we have to exclude all the numbers divisible by p. So we have 0 times p, 1 times p, 2 times p, and so on. And if I take p to the k minus 1 times p, well, this one is p to the k, so I should not consider this one. So all the elements that are smaller than p to the k and are not coprime with p are listed here. And how many elements are there? Well, I start counting from 0, 0, 1, 2. So there are exactly p to the k minus 1 elements here. Because here will be p to the k minus 1 times p. So here, p to the k minus 1 elements. Okay? So that's why here we have p to the k minus 1 times p minus 1 element. This is the amount of elements in this group because we subtract this amount. So this group will be isomorphic to the cyclic group with this amount of elements. So the claim says that for any odd prime number, this group is cyclic. Moreover, it's possible to find a generator here. So let me explain how to do this. Well, suppose we're given an element A from z p to the k star. Then this element is a generator if and only if the following two conditions are satisfied. We have two conditions. The condition number one, well, first of all, A is a remainder modular p to the k. So we can take it modular p. Let's take it modular p. Then it must be a generator in zp star. This is the first condition. And the second condition, if you raise a to the p minus 1, it must not be equal to 1 modular p square. Well, as you can see, the conditions are not pleasant. That's one of the reasons why I don't want to prove this, because like the proof itself, it doesn't teach you anything except some tricks with integers, and that's not very interesting in our case. But in general, what you should know is that this group is cyclic, and if you ever need to find a generator for this type of groups, this is the way. Because like this group is, well, it's much smaller than the initial one because there are only p minus 1 elements here. So somehow you can brute force this by finding a generator. So you can find all the generators here. And then for each generator, you just compute a to the p minus 1, and it must not be 1 modular p squared. This is just the second condition you have to check. So this is the way how to find a generator for this kind of group. Okay, now, are there any questions regarding the statement? Should I clarify something? Okay, good. Now, the next case is the case of even prime numbers. Suppose p is equal to 2. In this case, the group z2 to the n star is not cyclic, but it's a direct product of two factors. So you see, again, if you use this formula, well, this formula also works in order to count the amount of elements. So it's 2 to the power of n minus 1, and that's it. So this is the amount of elements here, 2 to the power of n minus 1. And here you have 2 elements, here you have 2 to the power of n minus 2, and when you take the product, you will get exactly 2 to the power of n minus 1. So the amount of elements is at least the correct one. And here we know exactly the generators. So if you take the element 1, 0, it corresponds to the element minus 1. Well, saying minus 1, I mean the inverse element to the remainder of, well, the inverse element to the element 1 with respect to addition. But okay, so it should be written as 2 to the power of n minus 1, but it's easier to represent such an element as a minus 1, okay? So, like, strictly speaking, you should take 2 to the power of n minus 1. This is the element I'm talking about. And the second element corresponds to 5. So every element here can be presented in the form -1 to the a, 5 to the b, where a is between 0 and 1, and b is between 0 and 2 to the power of n minus 2. And this element corresponds to the pair AB. So this is how the isomorphism works. So it's not cyclic, but it's almost cyclic. And here is the list of the explicit generators. So this is the second claim. So now, using this tool and these two claims, well, at least you can find the decomposition of every group of this form into a product of cyclic ones. And as you can see, there are almost, well, the amount of factors here is almost the same as the amount of primes. So each odd prime gives you exactly one factor, and the prime being 2 gives you 2 factors. So this is how it works. Okay. And this is basically all I wanted to say about finite abelian groups. So now we're ready to switch to a brand new topic. But before doing that, are there any questions regarding finite abelian groups, or probably anything written here, just in case? Okay. Now, cryptography. Well, I want to start with a description of a general issue we're fighting with. So suppose there is you, there is your spouse, and there is your lover. 3 actors, as usual. And you have a message. Okay? Well, just an innocent one, like nothing special. And you want to send this message. But what is the problem? Let me show you the problem. Here is one. Your spouse has a very special tool. And if you send this message as it is, there's a big chance this is your final message. Like literally the last message in your life that you will send to anyone. So we have an issue. We have to solve this issue. And how to do this? Well, the idea of encryption and decryption is based on the following observation. Well, it happens, like it's just some occasional fact, like no one knows why it happens, but it happens that sometimes you have a map between 2 sets, like x and y, and you have a map. And it could be a bijection, it doesn't matter currently, like let's say it's a bijection. And if you want to compute this map, well, it's very easy. It's easy to compute. Well, no one can say exactly what it means easy, but like it's fast. Like you don't have to wait like 1 million years in order to find an image of a point x. Like in a couple of seconds it can be done. But if you try to find the F inverse, this guy is very hard to compute. What do I mean by hard? Like, well, the only way to compute this thing is to go through the list of all the elements here and just check if this guy goes to the element you want to find the preimage. For example, if you are given an element y here, the only option for you to find its preimage is just to go through all of these elements and check if this element goes to the required one. So just the brute force is the only solution. And this is the most optimal solution. Well, no one can prove that these kind of maps exist, but there are some cases where we believe that we have found a map with this property. And now, how to use this map? Well, usually you can somehow adjust this information, and you can somehow produce a new map with a better property. What is the better one? Like you have a map and you have some like additional argument, which is called a key. So if you know this key, then the map can be applied like in seconds. But if you don't know this key, it's very hard to apply the map. And this is the idea how to encrypt and decrypt information. If you know some secret information, you can do some operation very quickly. But if you don't know this information, well, the only option for you is just the brute force. And if there is like 10 to the 10 to the 10 to the 10 of elements, there is no way to do it in, like using brute force. So this is the basic idea. Okay, now I want to give you an example of a map with this property. Well, let's start with a discrete logarithmic problem. What is this? Suppose we are given the group G. And an element G small from G capital. Now there are two operations. First of all, if you are given an integer, you can raise G to the power of n. This is the first operation. For an integer n, we can produce an element of the group G, which is the nth power of G. And we consider this operation to be fast. I will explain in a minute why. But there is like an inverse map. Suppose you're given an element H from the group G, and you want to find an element n such that G to the n is equal to H. Well, so this operation is always fast, but the second one need not be. I mean, it could be fast. I'll give you an example. But sometimes this operation, well, is really hard to execute because the only option for you is go through all the possible integers n, and only then you can find well, an appropriate solution. Like sometimes it's hard. So it's very important that just sometimes, because if you are not accurate, so your group G was chosen like randomly and the element G small was chosen randomly, well, like it may happen that it's also fast, but sometimes it's hard. Now, examples. Example number 1. Let's take G capital to be Z plus. Okay? And G small is the element 1. What does it mean to raise an element to a power in this group? Like G to the n, by definition, is like G plus G plus G n times. So in our case, G to the n is just n times 1. It's easy to compute, like. But now, suppose you want to find this problem. So if your element H is given to be m, now you want to solve an equation. Try to guess how hard it is to find the element n. It's just m. So this is an example of a group G and an element G small, where both problems are fast. Both maps could be computed very quickly. Now, another example where the computation is not hard. The same thing happens when you take Zn with addition. Let's say again, here G small is 1. Oh, well, there are maybe other generators here. Every integer coprime with n will be a generator, but let's take G being 1 in this particular case. Again, raising to a power will be multiplying, let's say k, because n is already taken here, so let's say k. So raising to a power is just multiplying 1 by k, and then we take the result modular n. So it's not that difficult. But in the opposite direction, if you are given an element m from here, well, you have to solve an equation like that. And again, it's simple because you just need to take k to be m, and that's it. So this is an example where, again, it's not very complicated. So we need a better example. So let me show you a better example. And this is Zn star. Okay. Well, yeah, an example number 3. Zn star with multiplication. This is your group G. And suppose G small is some element from G capital. So we already know that this group need not be cyclic, but it's a product of cyclic ones. What we could do, we could take something like Zp to the n star, where p is an odd prime, then this group is cyclic. And we could even take G to be a generator. Okay? But in general, we may just consider an arbitrary n and an arbitrary element G here. Now, well, in this case, in order to raise G to a power, we should compute, yeah, and let's denote it by a, like a remainder. So we should compute a to the n, bad again, a to the k modular n. So I will discuss in a minute how to compute this quickly. We can actually use fast squaring algorithm, and we can do it in log k operations. Are you familiar with the fast squaring algorithm? Is there anyone who doesn't know the algorithm? Okay, that's good. So yeah, so there is a way how to do this in O log of k. So that's why it's quick, because of this algorithm. But now, if you're given an integer b from Zn star, and you want to find k from z such that a to the k is equal to b, then, well, now here is a funny thing. No one knows how to solve this problem like any way but using brute force. Like literally, there is no algorithm, there is no way how to solve this problem without like choosing all possible k's and comparing the result with b. So this is an example of an operation that is hard to do without brute forcing. This is hard. Okay, how hard it is? Well, it depends on the choice of the element a. For example, if you take a to be 1, then all powers of the element a are just 1s. Well, and it's obvious that if you're given an element b which is not 1, there is no such a solution. And if you're given b to be 1, then k is just any number. It's not interesting. So this is a poor choice of an element. But if you're given a, well, so why this is a poor choice? Because, well, you have too few powers. Because let's say you're given an element A such that it has only 3 different powers. Then it's not hard to solve such a problem. Because if a cyclic group generated by A consists of 3 elements only, like if you're given an element B, which is not here, then there is no solution for this equation. And if your element B coincides with one of them, you already know that this guy is some power of A, this is another power of A, and this is another power of A. And you can solve it almost immediately. So when solving this equation is an issue, when this list is huge. So what we need, that the size of the cyclic group to be as big as possible. So that's why usually people try to take this element G as a generator of the group you are given. So in this case, there is a generator, and this is the best choice for you because the list of powers will be the set of all elements here, making it harder to brute force through all the powers of the element G. So, so here we have an example of a group G and an element G small, such that the first problem is quick and the second one is hard. But the hardness of this problem depends on the choice of element G small. So still, having this group G, you have to take like a good element G small. Okay.
Can we quickly find such?
What again?
Can we quickly find such generator?
Well, it doesn't matter if it can be done quickly because well, you have to do it just once. Because when you have this element, like you just fix it and you use it, you have no intention to change this element. Like so, if you spend like 1 month using like supercomputer to find such an element, it's okay for you because then you will use this element like to the rest of your life. It doesn't matter. And if you know at least one generator, then you can find any generator because we know how to recompute all the generators of the cyclic groups. So because you are not doing this on the fly. Now, that was some mathematical foundation for the cryptography. I want to discuss some implementation details. But before doing that, let me see if I want to explain something else here. Okay, no. That's fine, that's fine. Okay, now, so cryptography, how it works. So again, well, usually, well, your message is encoded in some alphabet. Let's say your message is a string in an English alphabet. Well, it has nothing to do with any group or anything we discussed yet. So it's just a string. Before doing any encryption or decryption, you should translate this string into a sequence of elements of some fixed group. So you should fix a group G and an element G small. We just fix them. Fix them. Now, if you are given a string, you should translate this string into a sequence of elements of the group G. Let's say you have like a very, very long sequence of elements. You can split a long sequence of symbols. You can split the long string into small pieces of a fixed length, and then if there are as many strings of this length, as many elements in the group G, you can map strings of a fixed size to the elements of the group G. Okay? So what's written here, you have a string of a fixed size, let's say k, and you map this piece into an element h1 of the group G. Then if you have a second piece of the length k, you map it to the second element of the group G, and so on. So you just encode strings of fixed length by elements of the group G. And this rule is well known. So everyone knows this. You know, your spouse knows, your lover knows, like everyone. This is just a part of the protocol. This is an open information. There is no encryption or decryption here. Like everyone can do this translation. That's not big of a deal. But now, here, like if you want to encrypt an information, you can apply some algorithm here and change this sequence of elements of the group G by another sequence, let's say M1, M2, and so on, Mk. And this is your encryption. So this is the part where all the magic happens. So all the magic happens with the elements of the group G. Because for an outsider, this will be just a random sequence of elements of the group G. If you try to apply this rule to these elements, you will get some nonsense. It won't be the initial text. And then, if you want to decrypt this information, you apply another rule, and you can recover the initial sequence of elements. And then, using the same rule, but in the opposite direction, you just translate each element of your group into a piece of a string of the length k, and then you will get your text again. So this is the text. And this is what your lover gets. Okay, so this is the general rule how to apply encryption and decryption. First of all, when you have initial message, you have to translate this message to the language of your encryption system. Currently, we will deal with elements of a group G, so we have to translate our strings to the elements of the group G. Then, on the level of the group, we have encryption and decryption. And then, when you want to obtain the initial message, you just want to translate it back to the strings. Well, this is the general thing. And now, I want to be focused on this central part, because this is the interesting thing. This is like something, you have a table and you just translate like sentences into elements of the group, but this is an interesting part. So there are many approaches how to do this, but all of them are based on the functions with that property that you can do something very quickly in one direction, but it's very hard in the opposite direction. Okay, let me show you how to do this. Okay. Diffie-Hellman. How many L's? Okay. Well, now, let me draw this picture again. So we have three agents here. Now, in order to communicate safely, we need to fix a protocol. What does it mean we need to fix a protocol? What is the part of a protocol? Well, this is a well-known information. This information is known by everyone. Well, we should fix a group G. Its generator G small. We should be able to compute its order. And we should fix this translation table. I will skip this translation table, but other than that, the well-known information is the group G, an element G small, and the order of the element G small. We assume that everyone knows this information. Now, we want to communicate. Well, how to communicate? Usually, every communication consists of two steps. The step number one is to establish communication. And by establishing communication, I mean we should produce some secret information, like common secret information, in such a way that the man in the middle cannot recover this information. But, well, the best way to do this, well, you can buy a ticket, okay, on a train from Moscow to New York, go to your lover, like tell him or her the secret information, and then go back, for example, by swimming. That's also fine. And then you have this secret information. How cool is that? Not very much. Also, assume that every time when you have to log in into a banking app, you have to go to the bank and tell the secret information, or the bank have to tell you secret information. And then you can go home and like type the secret information, and then you can start the communication. It's very inconvenient. So you have to find a way how to produce this secret information using this open channel where everyone can listen to you. Okay? Well, here's an idea. First of all, you should generate some secret number A. What is A? A will be an element from Zn. So it's a remainder modular n, where n is exactly the order of the element G. Your lover must invent a secret element from Zn. Well, if you want this, if you want the whole system to be more reliable, you want actually A and B to be co-prime with n. Well, let me put an asterisk here, but using blue color. So, I mean, this is not very important, but you don't want A to be 0, for example. It's like a stupid thing to do. So basically what you want A to be an element here co-prime with n, and B a random element here co-prime with n. And you want n to be huge, like thousands of ciphers. Okay, thousands of digits. Okay, now, then you produce what's called a public key. What is a public key? Public key is G to the power of A. And your lover produces its own public key, G to the power of B. And then you send your public key to your lover, and your lover sends his or her public key to you. So you tell to everyone your public key. So now your spouse knows these elements. So you receive this element S here and R here. Now, here's one remark. Here we know that the element S is of the form G to the A. But here we don't know the element A. In order to find the element A, we have to solve exactly the discrete logarithm problem in this particular group. We have to find an element A such that G to the A is equal to S. So we believe that this is a hard task. So we believe that it's impossible to recover the integer A just looking at the element S. So that's why when we send the element S to everyone, well, no one knows the element A. So this is still a secret information. It's not revealed. It doesn't matter that everyone knows S. So that's why it's a public key. And the same happens here. Only the lover knows the element B, but we know the element R. Now, using these public keys, now we can produce a secret key. Well, let's take the element R here and raise it to the power of A. What will it be? Well, we know that R is an element of the form G to the B. Well, we don't know the element B, but we know it must be of the form G to the B. So the result will be G to the A times B. And in this case, yeah, we take S and raise it to the power of B. And again, since we know that S must be of the form G to the A, this element is also in the form G to the A times B. So that's why we can produce a common element, K. So this is the element that only me and my lover knows. No one else can produce the same element. Because in order to produce this element, well, you must know either element A or element B or A times B. And it's impossible to recover this information using the public keys, because from the public keys, in order to recover A and B, well, you have to solve this hard problem. So this is the step number 1, establishing communication. So now, after this step, you and your lover have this secret element, common secret element. By the way, if element A was taken from Zn star and B was taken from Zn star, then if G is a generator, if G has order n, then G to the A also has order n. And G to the A times B also has order n. So the order of the element K is also n. The order of each public key is also n. So, I mean, technically, this is, well, like for the whole scheme, it's not very important, but if you want this to be reliable, like this is an important property to check. So this is what we want. That's the reason why we want to take A to be here Zn star. Because you see, if A was 0, then your public key will be 1. Like it's compromised already just by definition. Okay, so again, that was the step number 1. There was no communication yet. So we didn't pass any message. So now we want to send a message. So let me show you how to send a message. Okay, now you suppose lover. Okay, here is this common knowledge. I believe I should switch to a different marker. So we have A from Zn star, we have B from Zn star, and we have this K, which is, so this is the situation we're in. Now, what is an information? An information in our case is just an element of the group G. Let's say you want to send a message H, which is an element of the group. So the message now is an element of the group. Like, that's it. It's not a string. It's already a converted string to the element. Now, you want to encrypt the message. How will you do that? Well, you just multiply this element by the secret key. Well, for example, on the left, on the right, it doesn't matter, because, well, actually, in general case, if G is not commutative, it could matter, but usually people use abelian groups in this case. But okay, let's say you multiply it on the right, on the left, by key. And then this is your message, encrypted message. And you send the element M here. Well, you see, in order to recover the element H, you need to know K. Like otherwise, you have to go through all the elements of the group G, well, as K, and then you try to apply this table of translation in order to check if it's some meaningful message or just a random strings of symbols. Now, when your lover gets this message, in order to decipher the message, you just divide by K on the left. Now, I'm sorry, the other way around, MH, because like I want to recover the H, not the M. M is already given. Now, what does it mean divide by k on the left? Well, you should compute the inverse element of the element k and then multiply on the left. Well, now, how to compute the inverse element? Well, sometimes it's easy. Well, for example, if you're given a group where you know the exact rule how to compute the inverse element, you just apply this map. And usually this map works quick enough. But there is a universal way, because you know the order of the element k is n. Well, in general, if a is not here and b is not here, the order of k divides n. So k to the power of, let's say, k to the power of n is always 1. In particular, k times k to the n minus 1 is equal to 1. So that's why this element is k inverse. So if you don't have an algorithm to compute k inverse, you can again use the raising to the power algorithm in order to find the inverse element. I mean, it's not a very pleasant thing to do by hands, but for a computer, like, it doesn't matter. That's one of the way how to find the inverse element. But in some groups, you have better options. Okay, this is how to invert the element, and this is how to restore the initial message. So now you just apply this algorithm to every element from the group G and just send all of them there. So this is the way how to communicate. And if you want to send some message back, you apply exactly the same algorithm. So this is how it works. So this was a communication. So the communication process is very simple. You just multiply and divide by the secret information. So this is exactly this key element that I meant here. Okay, so just in case, who think that the whole process of communication or establishing the communication and the sending message was clear? Okay, are there any questions regarding the process? Okay, good. Now, let's discuss some properties of this system. You see, usually when you want to attack a system like that, you want to collect some information, and then using this, like all these messages, you could try to find this private key, and there are different ways how to do this. But what it says to us, it says that it's not a good idea to have the same key all the time. Like, the longer your communication works, the worse it will be, like, in terms of protection. Like, it's better to change your key like in several iterations. The exact number depends on the system, but there is a simple way how to do this. For example, you may establish some communication, then like for 100 messages you use this public key, then you reestablish your communication with other public keys, and then you have different private key, and then you use this private key for other 100 messages, and so on. This is one way of doing this. There is a better way. So let me explain the way how to improve the whole process. So the problem with this approach, when you have 100 messages with the same key, is, are you sure that 100 messages won't compromise your system? Like, maybe you should use like 10 messages or just 2 messages, but when you use just 2 messages, it's not a good system. Like, if you can be compromised after 2 messages being sent. So what you can basically do, you can change your private key every time you send a message. But like, you know, when you see some advantages, it's a very rare case that you don't have a disadvantage. Like, if we will change our private key all the time when we send a message, there must be some, like, how to say, a kind of pitfall. So in this case, we have a two-way communication. It doesn't matter who wants to send a message, because you and your lover, you both have this secret information, and you use this information in order to encode and decode the messages. And you can send them in one direction and in the other direction. The system I want to present now is very similar to this one, but it's a one-direction system, which means that only one person can send messages to another one. So one-direction system works like this. Again, so this part is the same. So we have to use this group G, the element G small of the order G capital. Now, the first step is to establishing a connection. And this will be a one-way connection, which way, let me say, okay, assume that you want to send a message. So how it works? Well, you need an invitation to send a message. In order to generate an invitation, your lover generates an element B from Z and star and generates a public key R being G to the B. And then she or he sends this public key to everyone, and you receive this public key. So this public key, like, could be considered as an invitation. Please send me the information using this public key. And now you can send the information in the opposite direction, but you cannot receive. If you want to receive the information, you could start with the same procedure. You could send your public key, and then you can receive the information. So that's why the system is it works in one direction. So this is the first step, establishing a communication. So now we have an invitation. So suppose we want to send a message, like H1, H2. Like, there are like two elements of the group, because I need at least two elements, because I want to send a sequence of information, and I want to show you how to change the key, how to use a different key for each element here. So for each element here, you want to produce this secret number A. So you randomly choose, in this particular case, two random elements. So an element A1 from Zn star and an element A2 from Zn star. Okay? Now, for each number here, you produce the secret key. K1 will be R to the power of A1. K2 will be R to the power of A2. Okay? And now you use this private key in order to encrypt this message, and this private key in order to decrypt this message. Okay? So K1 times H1 and K2 times H2. So this will be decrypted messages, and you will send them. But now, your lover must have a way to recover this information. But in order to recover this information, she or he needs the knowledge of your public key. So together with the message, you will send the public key corresponding to this element. And what is the public key? The public key will be G to the power of A1, and here G to the power of A2. So you send a pair. So each time you send a new public key and a message encrypted by this specific private key. So now, when we want to decrypt this information, first of all, for each step, we must produce the corresponding private key. In this case, we just raise this public key to the power of b. This is what we can do. This is how we get the private key for each pair. And then, in order to decrypt the message, we just divide by k1 the first element, and by k2 the first element of the second pair, and so on. So that's why we can recover h1 and h2. So the difference here is that for each message, you should generate the secret integer a, and for each integer a, you generate public and private key. You use private key to encrypt the message, and you send a pair, the encrypted message and the public key, to the other side. So this is how it works. This system is usually called Algebra system. The original one is Diffie-Hellman system, but the names, they do not matter. The most important thing is to know how it works. Okay, so this is a better, so this is one way how to improve the system, how to make this choice of keys random. For example, if somehow some choice of an element here wasn't good, like since you change them randomly, well, the probability of taking a bad element A here is not that high, and like it happens only for one specific case, for one specific message, so it's much better. Like and when I'm saying something like it's much better, like it's like more robust, what it means exactly? Well, it means no one knows what it means. Like we believe that it's more robust, it works better. We have some like experience that it works better, that people cannot like compromise the system longer than the other one. So there is no strict proof. Well, there are some literature trying to formalize the theory of encryption and decryption. They try to prove some results saying that, well, this task is hard if we're given this and this, and it's hard in this specific sense. But like it's still, this theory is not good enough, so it's not worth even mentioning. So, and if I try to formulate like something very simple, there will be like 200 lines of a claim, and it will be impossible to understand what they're trying to say. But basically, what they're trying to say that this task is well, this system is hard to compromise, and then just like 200 lines in what does it mean exactly hard to compromise, like a formal definition. Okay, we have 10 minutes. Let me explain another system, RSA. Are you familiar with RSA system? Just in case, who think that it was clear how the one-way communication works, just in case? Are there any questions regarding one-way communication? Okay, who is familiar with the RSA system? Okay. Let me show you another way. Yeah, but by the way, in general, here we use ZP star. Like, if you want a good example of the group G, there are actually two candidates currently. One candidate is ZP star for a prime number P. There is a reason why we would like to use a prime number, not a power of prime. And the second example is an elliptic curve over a finite field. So that the second example gives you a more robust system, and it explains why you need some abstract algebra, like because, well, in order to explain what an elliptic curve is, you have to know some algebra. But it produces a better system. It's more fragile in a way that if it's easier to make a mistake and produce like a bad system, which is easily compromised. But if you know how to do this, it gives you a much better solution. Okay, RSA. Well, the main reason why this system works is because the discrete logarithm problem is hard So it's hard to find A such that G to the A is S. There is another task which is also hard, is factoring a number. So if you are given an integer, it's really hard to split it into a product of primes. Like, there is no better way than just go through all possible primes and just divide it until you're done. So, so what is hard? Okay, so the operation in one direction. If you're given two numbers, so it's easy to produce the product. But if you're given a number, it's hard to split it into a product of primes. Now, here is an idea how to use this. Let's take two huge prime numbers. P and Q are prime. And they're huge, like thousands of digits. Now, let's produce the product. And I want to take a look at the group Zn star. Okay. Now, if you're given an element here, H, you can raise this element to a power. Let's say you can take H to the power of E. Okay. But now, it may happen if E is a good enough element, you can raise it to a power again, and you will get initial element H. Okay? When it happens? Well, let's take a look. Well, it happens when this happens. Okay? But what does it mean exactly? Well, if you divide by H, it means that H to the power of ED minus 1 is equal to 1. Well, how to guarantee that this equality holds? Well, one way is to produce two integers E and D such that E times D is equal to 1 modular the size of this group. Well, the size of this group is what? Well, this is what's called the Euler function of n. So, and as we already know, by the Chinese remainder theorem, this will be ZP star times ZQ star, and this one is a cyclic group ZP minus 1, and this one is the cyclic group ZQ minus 1. So the amount of elements here is P minus 1 times Q minus 1. So I will write phi of n, where phi of n is P minus 1 times Q minus 1. Okay? So why, if this is true, then this holds? Let me explain. So suppose that this equality holds. Then what it means E times D is equal to 1 plus n phi of n. Okay? Then if you raise H to this power, H to the power E times D is equal H to the power of 1 times H to the power of phi of n to the power of n. N is just a fraction. Like when you say that this one is equal to this one modular this guy, it means that this guy is equal to 1 plus this guy times something, and this something is n. This is just an integer such that you get this equality. Okay? So now, when you have this equality, you see phi of n is the size of this group. By the corollary of the Lagrange theorem, we know if you have an element of the group, and if you raise this element to the power of the size of the group, you will get 1. So this thing here is just the neutral element. So that's why the result will be H. So exactly what we wanted. Okay? So again, let me repeat what I wanted to say. if we're given this group and an arbitrary element h and two integers e and d with this property, then raising to the power of e replaces the element h by something else, and again raising by the power of d, we will get the initial element h. So these are two operations that are inverse to each other, and this equality guarantees that these two operations are inverse to each other. Okay? Now, let's use this information in order to produce the communication system. And I have like 5 minutes left. Okay, you suppose you love. The common information is, the secret information that only you knows, P and Q. Everyone knows Z n star. So the element n is known to everyone. Now, only you know the number phi n. And now you have to produce two elements E and D such that this equality holds. Okay? So you produce these elements E and D such that these holds. Well, you could take E and D to be 1. That's not an interesting case. So you have to be careful in this specific place. So you want to take something non-trivial like big integers E and D. Now, what is a public key, by the way? Should I write something else? No. So, and now you want to tell to everyone the element E. So let me show you the secret information. The secret information is here, P and Q. No one knows this element, phi of n, and the element D. So why P and Q are secret? Because if you know the element n, in order to recover P and Q, you have to split n into factors. But this is a hard task. We have chosen P and Q in such a way that it's hard to factor n. So it's impossible to know these numbers. Now, if you want to compute this function, the only way to compute this function is to find this product. But in order to find this product, you need to know P and Q, because otherwise you cannot find P minus 1 and Q minus 1. So it's also impossible to recover this thing. And since you, and here. And now, since you don't know the modulus and the element D, it's impossible knowing the element E, find the element D, because you don't know what the modulus here. That's why it's impossible to recover D. So this information is secret. Now, this system is also a one-way communication system. So sending this E is the same as sending an invitation. Please send me an information, okay? So this was an establishing of the communication process. So you do all this work and send this element E to your lover. Now, if your lover wants to send you a message, what is a message? Message here is also an element of the group Zn. So we have H from Zn star. Now, when we want to encrypt this message, we raise H to the power of E. This will be M. And we send this message to everyone. And when we receive this message M, if we want to decrypt the message, well, because of this property, it's enough to raise this element to the power of D, and we will get the initial message H. So this is how it works. So this is the RSA system. So it's based on the assumption that it's hard to split a number into a product of primes. And if you want this task of splitting to be really hard, you want P and Q to be very close prime numbers. Well, there is a notion of twin prime numbers, like when the difference between them is 2. So this is your best choice. Well, this is how you use it. Okay. Okay, yeah. So this is the one-way communication in this direction. So this is the last system I wanted to present today. Are there any questions regarding this system? Okay, then that's it. Thanks for being here.